The universe is a vast and incomprehensibly complex place, filled with countless mysteries that continue to baffle scientists and astronomers. Among these mysteries, the formation and fate of planetary systems stand as some of the most compelling. How do planets come to be? How do these systems evolve over billions of years? What eventual fates await the planets that orbit distant stars? These are questions that have sparked curiosity and driven exploration for centuries. And though we've made significant strides in understanding, much remains unknown. What we do know, however, is that planetary systems are more dynamic and varied than ever imagined, with forces at play that shape their formation, evolution, and ultimate fate in ways both predictable and wildly unpredictable. But before we continue, if you like this type of videos, please subscribe to the channel and comment. To understand the formation of planetary systems, we must begin with the birth of stars. Stars are the engines of planetary formation, and without them, no planets would exist. The process starts in vast clouds of gas and dust known as molecular clouds. These regions, often spanning light years, are the cradles of star formation. Under the influence of gravity, pockets of gas within these clouds begin to collapse in on themselves, pulling in more and more material. As the pressure and temperature at the center of these collapsing regions rise, nuclear fusion eventually ignites, and a new star is born. Surrounding this newly formed star is a rotating disk of leftover material, a protoplanetary disk. These disks, composed of gas, dust, and ice, are the birthplaces of planets. Through a process known as accretion, particles within the disk collide and stick together, gradually forming larger and larger bodies over millions of years. These planetesimals, as they are called, continue to grow, and some eventually become full-fledged planets. The exact mechanisms of this process, though understood in broad strokes, are still an area of active research. For instance, how do these tiny dust grains manage to stick together when their initial collisions are more likely to break them apart? And how do these early planetesimals survive the turbulence of the protoplanetary disk? The structure of a planetary system can vary widely depending on the specific conditions present during its formation. Some planetary systems may form with massive gas giants close to their star, while others may form with small rocky planets like Earth at more distant orbits. The size and type of the central star also play a significant role in determining the types of planets that can form. For example, stars larger than the Sun may host systems with more massive planets, while smaller stars may harbor Earth-like planets in their habitable zones. Once planets have formed, their fates are tied to the dynamics of their planetary system and the life cycle of their parent star. Early in a star's life, the young planetary system is often a chaotic place. Planets may interact with one another gravitationally, leading to collisions, ejections, or changes in their orbits. Some planets may be hurled into their star, while others may be ejected from the system entirely, becoming rogue planets that drift through the galaxy without a host star. These early stages of planetary systems are marked by instability, and only a fraction of the original planets may survive to form a stable configuration. One of the most important factors in the long-term evolution of a planetary system is the behavior of gas giants. These massive planets, like Jupiter and Saturn in our own solar system, can have a profound influence on the orbits of smaller planets. Gas giants tend to migrate early in a system's history, moving closer to or farther from the central star. This migration can disrupt the orbits of other planets, pushing them into new orbits or ejecting them from the system. In some cases, gas giants may even prevent the formation of smaller rocky planets altogether by sweeping up all the material in the protoplanetary disk. The discovery of exoplanets, planets that orbit stars outside our solar system, has revolutionized our understanding of planetary systems. For decades, the solar system was the only planetary system we knew, and it was assumed that most other systems would be similar. However, the discovery of exoplanets has revealed a staggering diversity of planetary systems, many of which are unlike anything we had previously imagined. Some systems contain planets that are far closer to their star than Mercury is to the Sun, while others have planets with highly eccentric orbits that take them on long, elliptical paths. There are even systems with multiple stars, where planets orbit one or more suns in complex, often chaotic patterns. One of the most surprising discoveries has been the existence of hot Jupiters, gas giant planets that orbit extremely close to their stars. These planets, which are much larger than Earth, have been found in orbits that take them closer to their stars than Mercury is to the Sun. How these massive planets ended up in such close orbits is still a matter of debate. Some theories suggest that these planets formed farther out in the system and then migrated inward, possibly due to interactions with the protoplanetary disk or other planets. Others suggest that these planets may have formed in place, though this would require a very different set of conditions than those present in our own solar system. The fate of a planetary system is ultimately determined by the life cycle of its star. Stars, like planets, have finite lifespans, and as they age, they go through several stages of evolution. Our Sun, for example, is currently in the middle of its life, but in about 5 billion years, it will begin to run out of hydrogen fuel and expand into a red giant. During this phase, the outer layers of the Sun will expand, potentially engulfing the inner planets, including Earth. The outer planets may survive this expansion, but their orbits will be altered, and the entire system will be thrown into a state of flux. After the red giant phase, the Sun will shed its outer layers, leaving behind a dense core known as a white dwarf. This remnant will continue to cool and fade over billions of years. Any planets that survive the red giant phase will find themselves orbiting a much dimmer and cooler star. Over time, the white dwarf will continue to cool until it becomes a black dwarf, a cold, inert object that emits no light or heat. The planets that remain in the system will slowly drift away as the gravitational pull of the black dwarf weakens. However, not all planetary systems will meet this quiet end. In some cases, interactions between planets or with other stars may lead to dramatic changes in the system's configuration. For example, if a star passes close to a planetary system, its gravitational influence could disrupt the orbits of the planets, causing them to collide, be ejected, or be pulled into the star. Such interactions could also lead to the capture of rogue planets, which would then become part of the system. The discovery of planetary systems around other stars has also raised questions about the potential for life beyond Earth. The search for habitable planets, those that could support liquid water and, by extension, life as we know it, is a major focus of modern astronomy. The habitable zone around a star is the region where conditions are just right for liquid water to exist on a planet's surface. In our solar system, Earth is the only planet in the habitable zone, but around other stars, there may be many more Earth-like planets waiting to be discovered. One of the most exciting recent discoveries is the potential for habitable planets around red dwarf stars. These small, cool stars make up the majority of stars in the galaxy, and many of them are known to host planets. Because red dwarfs are much cooler than the Sun, their habitable zones are much closer to the star, meaning that any potentially habitable planets would orbit very close to their star. However, red dwarfs are also known for their intense stellar activity, including powerful solar flares that could strip away the atmospheres of any nearby planets. The question of whether planets around red dwarfs could support life is still an open one, and it is likely that future observations will provide more answers. As we continue to discover new planetary systems and learn more about their formation and evolution, it becomes clear that the universe is far more diverse than we ever imagined. Every new discovery challenges our understanding of how planets form and what their ultimate fates may be. From the chaotic early stages of planetary formation to the slow, quiet death of a star and its planets, the story of planetary systems is one of constant change and evolution. The vast diversity of planetary systems points to a broader understanding of how fragile and dynamic the cosmic processes truly are. Planetary systems, though governed by predictable physical laws, often defy our assumptions about stability and permanence. Over billions of years, planets shift, their orbits evolve, and entire systems can be drastically reshaped by forces both internal and external to their star systems. Even the seemingly tranquil planets of our solar system experienced periods of chaos, and their futures remain uncertain. One of the most intriguing aspects of planetary system formation is the concept of planetary migration. In the early stages of a system's development, massive planets, especially gas giants, often migrate from the outer regions of their solar systems to much closer orbits. This migration is thought to be caused by interactions with the protoplanetary disk. As a gas giant forms, its gravity interacts with the surrounding disk of gas and dust, creating waves in the disk that pull the planet inward. This process can lead to dramatic changes in the system's architecture, as migrating planets may disrupt the orbits of other planets, or in some cases, prevent smaller, rocky planets from forming at all. The phenomenon of planetary migration is particularly important in explaining the existence of hot Jupiters, gas giants that orbit extremely close to their stars. These planets are much larger than Earth, yet they orbit their stars in just a few days, meaning they are incredibly close to their host stars, far closer than the gas giants in our own solar system. This was one of the most unexpected discoveries in the early days of exoplanet research and forced astronomers to reconsider their models of planetary formation. Traditionally, it was believed that gas giants could only form far from their stars, where temperatures are low enough for gases to condense. The discovery of hot Jupiters showed that planetary systems could evolve in ways that were previously unimagined. In addition to migration, gravitational interactions between planets can also shape the evolution of a planetary system. Over time, these interactions can lead to what is known as orbital resonance. This occurs when the orbital periods of two or more planets are related by a ratio of small whole numbers, such as 2:1 or 3:2. When planets are in resonance, their gravitational pulls reinforce one another in a regular, predictable way. This can stabilize their orbits over long periods, or in some cases, cause their orbits to become chaotic and unstable. Orbital resonance is seen in our own solar system. For example, Jupiter's moons Ganymede, Europa, and Io are in a 1:2:4 resonance, meaning that for every orbit Ganymede completes, Europa orbits twice, and Io orbits 4 times. This resonance helps keep the orbits of the moon stable, despite the strong gravitational forces at play. However, in other systems, resonances between planets can lead to instability, causing planets to be ejected from the system or collide with one another. While gravitational interactions between planets can shape their orbits, interactions with other stars can also have profound effects on a planetary system. The universe is a dynamic place, and stars do not remain in isolation. Over time, stars pass near one another as they orbit the center of the galaxy. When a star passes close to a planetary system, its gravitational pull can disrupt the orbits of planets, causing them to be flung out of the system or drawn into the star. These close encounters are rare, but over the course of billions of years, they can have significant consequences for the fate of a planetary system. One of the most dramatic outcomes of such encounters is the creation of rogue planets. Planets that have been ejected from their systems and now drift through space without a host star. Rogue planets are incredibly difficult to detect, as they emit no light of their own and are not illuminated by a nearby star. However, their existence is almost certain, and some estimates suggest that there may be as many rogue planets in the galaxy as there are stars. These lonely worlds, drifting in the cold darkness of interstellar space, are one of the most mysterious and intriguing aspects of planetary system dynamics. The eventual fate of a planetary system is inextricably linked to the fate of its star. As stars evolve, they go through several stages that can drastically alter the environments of their planets. Our Sun, for example, is currently in the main sequence phase of its life, steadily burning hydrogen in its core. But in about 5 billion years, it will exhaust its hydrogen fuel and begin to burn helium, entering the red giant phase. As it expands, the Sun will grow so large that it may engulf the inner planets, including Earth. Even if Earth survives this expansion, its surface will be scorched, and any remaining life will be eradicated by the intense heat. The outer planets, such as Jupiter and Saturn, may survive the Sun's expansion, but their orbits will likely be altered. The outer layers of the Sun will be blown off into space, creating a planetary nebula, and the remaining core will become a white dwarf. This small, dense remnant will continue to cool over billions of years, eventually becoming a black dwarf, an object so cold that it no longer emits any visible light. The planets that survive will find themselves orbiting a dark, cold remnant of their once bright star. For planets around more massive stars, the fate is even more dramatic. Massive stars, many times the size of the Sun, live much shorter lives, burning through their nuclear fuel in just a few million years. When they reach the end of their lives, they explode in supernovae, releasing an enormous amount of energy and material into space. Any planets close to the star are likely to be destroyed in the explosion, while those farther out may be stripped of their atmospheres or ejected from the system entirely. The core of the star may collapse into a neutron star or a black hole, leaving a strange and hostile remnant behind. Even after the death of a star, the planets that survive may continue to evolve. Over time, the gravitational influences of other stars, rogue planets, or even black holes could alter their orbits, leading to new configurations or, in some cases, destruction. In some systems, planets may be pulled into the remnants of their star, either spiraling into a white dwarf or being consumed by a black hole. In others, the planets may drift further and further from their star, eventually becoming rogue planets themselves. The long-term future of planetary systems is still a matter of speculation, but some theories suggest that in the distant future, billions of years from now, most planets will be ejected from their systems as stars die and galactic dynamics continue to evolve. These rogue planets will wander the galaxy, perhaps for eternity, as the universe slowly cools and fades. The study of planetary systems, both in our own solar system and beyond, has revealed a universe far more complex and dynamic than we could have imagined. The discovery of exoplanets has shown us that the processes that shape planetary systems are varied and often unpredictable, and that the ultimate fate of any planet is tied to the chaotic forces at play in the cosmos. But beyond the scientific curiosity, the study of planetary systems raises profound philosophical questions. What does it mean for a planet to be ejected from its system and wander alone in the void? Could life exist on such a world, cut off from the warmth and light of a star? What will happen to our own solar system in the distant future, and what will be the fate of Earth? These questions remind us that our understanding of the universe is still in its infancy. For all our advances in technology and knowledge, there is still so much we do not know about the formation and fate of planetary systems. The mysteries of the cosmos continue to challenge and inspire us, driving our search for answers in the vast expanse of space. As we continue to probe the mysteries surrounding planetary systems, one area that demands particular attention is the potential for life elsewhere in the universe. The conditions under which planetary systems form, evolve, and ultimately meet their demise play a critical role in determining whether they might host life. This brings us to the concept of the habitable zone, sometimes referred to as the Goldilocks zone. This is the region around a star where conditions are just right, not too hot and not too cold, for liquid water to exist on the surface of a planet. Liquid water is considered one of the essential ingredients for life as we know it, and thus, identifying planets within this zone is one of the primary goals of exoplanet hunters. However, the habitable zone is not a fixed distance from a star. It depends on the star's size and temperature, and it can change as the star evolves. For example, in our solar system, Earth lies within the Sun's habitable zone, while Mars is near the outer edge, and Venus is just inside the inner edge. As the Sun ages and becomes a red giant, the habitable zone will move outward, possibly making Mars a more favorable environment for life, at least for a short time, before it too becomes uninhabitable. The shifting nature of habitable zones illustrates the dynamic relationship between a star and its planets, one that can dramatically influence the potential for life. But the habitable zone concept is not without its complications. For one, the surface temperature of a planet is not determined solely by its distance from its star. A planet's atmosphere plays a crucial role in regulating its temperature. Greenhouse gases, for instance, can trap heat and warm a planet, as we see on Earth and, to a much greater extent, on Venus. On the other hand, a lack of a substantial atmosphere can lead to extreme temperature fluctuations, as is the case on Mercury and the Moon. Additionally, the presence of oceans, land masses, and geological activity can all influence a planet's climate and its ability to support life. Another factor that complicates the search for habitable planets is the presence of gas giants in the same system. As we've already seen, gas giants can migrate from their original orbits, and in doing so, they can disrupt the orbits of smaller, potentially habitable planets. However, gas giants may also play a protective role, shielding inner planets from frequent impacts by asteroids or comets. Jupiter, for example, is thought to act as a sort of cosmic vacuum cleaner, its strong gravity pulling in or deflecting objects that might otherwise collide with Earth. In other systems, the presence of gas giants could similarly increase or decrease the likelihood of life depending on the circumstances. The discovery of planets around M-dwarf stars, small, cool stars that are the most common type of star in the galaxy, has further expanded our understanding of habitability. These stars have much smaller habitable zones than stars like the Sun, meaning that any potentially habitable planets must orbit very close to their star. This presents challenges, as planets in such close orbits are often tidally locked, meaning one side of the planet always faces the star while the other remains in perpetual darkness. This could lead to extreme temperature differences between the two sides, making the planet less hospitable to life. However, some models suggest that if such a planet has a thick enough atmosphere, heat could be distributed more evenly around the planet, potentially allowing for a habitable twilight zone between the hot and cold sides. The fate of planetary systems also ties into the question of life, particularly in the distant future. As stars age and change, the environments around them can shift dramatically. Planets that are currently habitable may become inhospitable as their stars evolve, while others may enter the habitable zone for the first time. These changes occur over billions of years, but they remind us that planetary systems are not static. They are always evolving. This brings up an intriguing possibility. Could life arise, go extinct, and then arise again on the same planet as conditions change over time? Moreover, the potential for life on moons, rather than planets, opens another avenue of exploration. Several moons in our own solar system, such as Europa, Enceladus, and Titan, are thought to harbor liquid oceans beneath their icy surfaces. While these moons lie far outside the Sun's habitable zone, the heat generated by tidal forces from their parent planets could create the conditions necessary for life. In this case, the traditional definition of the habitable zone may not apply, and life could exist in environments we once thought were too extreme. The possibility of life on exoplanets and exomoons is not merely a question of finding liquid water. Life, as we know it, depends on a range of factors, including the availability of nutrients, the stability of the environment, and the presence of a source of energy. In the search for extraterrestrial life, scientists look for planets that not only have water but also show signs of an atmosphere rich in elements like oxygen, methane, or carbon dioxide, which could indicate biological processes. The future of planetary systems, and the life they might harbor, is also bound to the ultimate fate of the universe itself. Cosmological theories suggest that the universe will continue expanding, with galaxies moving farther and farther apart. Over trillions of years, stars will eventually burn out, and the universe will grow cold and dark. In this distant future, even the most stable planetary systems will face inevitable doom. Stars will die, planets will freeze, and the very structure of matter may break down. This bleak end raises existential questions about the long-term sustainability of life in the universe. Yet, for now, planetary systems offer a glimpse into the potential for life and the mysteries that surround the formation of worlds. Each discovery, whether of an Earth-like exoplanet or a gas giant in a far-flung system, deepens our understanding of the processes that shape the cosmos. But with each new revelation comes new questions. How common are habitable planets? Are we alone in the universe, or is life a common outcome of planetary evolution? What will become of our solar system in the distant future? Our quest to understand planetary systems is far from over. We have only just begun to scratch the surface of what is possible. The future of planetary exploration holds the promise of discovering new worlds, learning about their histories, and perhaps one day, answering the age-old question of whether life exists beyond Earth. Until then, the mysteries of planetary formation and evolution will continue to challenge and inspire us, pushing the boundaries of what we know and what we can imagine. As we delve deeper into the evolution of planetary systems, it's essential to examine the various forces that govern their long-term stability and the potential threats that can disrupt them. Planetary systems are not permanent structures. they are influenced by a range of dynamic forces that can lead to significant changes over time. Some of these forces are external, such as gravitational interactions with other stars, while others are internal, stemming from the star and planets themselves. The interactions between these forces determine the lifespan of a planetary system and its ultimate fate. One of the most critical processes in shaping the future of a planetary system is stellar evolution. Stars are not static objects. They undergo various stages of evolution as they burn through the fuel in their cores. For a star like the Sun, this process takes billions of years, but it eventually leads to dramatic changes that can have profound effects on the surrounding planets. As stars age, they grow larger, brighter, and hotter, which can significantly alter the conditions on nearby planets. Eventually, a star like the Sun will enter the red giant phase, expanding to many times its original size. In this stage, the star's outer layers will engulf the inner planets, including possibly Earth, vaporizing them in the process. Planets farther from the star, like Mars or the outer gas giants, may survive, but their environments will be drastically altered. Once a star has exhausted its nuclear fuel, it sheds its outer layers, leaving behind a dense core known as a white dwarf. This marks the end of a star's active life, and the remaining planetary system will face new challenges. Without the intense radiation from the star, any surviving planets will cool dramatically, and their atmospheres may freeze or dissipate. Over time, the white dwarf will continue to cool and fade, eventually becoming a cold, dark remnant. At this point, the planets in the system, if any remain, will orbit a faint, dead star, with no source of heat or energy to sustain life. But the death of the star is not necessarily the end of the planetary system. Long after the star has died, gravitational forces will continue to shape the orbits of the remaining planets and debris. Over billions or even trillions of years, the gravitational interactions between planets, moons, and other objects can lead to significant changes in their orbits. Some planets may be ejected from the system entirely, becoming rogue planets that drift through interstellar space. Others may collide with each other or be consumed by the dead star. The long-term dynamics of a planetary system after its star has died is a fascinating area of research, and it raises questions about the ultimate fate of planetary systems throughout the universe. Another key factor in the evolution of planetary systems is the presence of binary or multiple star systems. In such systems, the gravitational influence of multiple stars can create complex and chaotic orbits for the planets. In some cases, planets may orbit both stars in a stable, circumlunar orbit, while in others, they may orbit just one star, with the second star exerting a periodic gravitational influence. These gravitational interactions can destabilize planetary orbits over time, leading to planetary ejections or collisions. Binary star systems present additional challenges for the formation of planets, as the strong gravitational forces can prevent the accumulation of dust and gas into stable planetary bodies. Despite these challenges, planets have been observed in binary systems, and understanding their formation and evolution is crucial for developing a complete picture of planetary systems in the galaxy. The future of a planetary system is also influenced by the presence of debris, such as asteroids, comets, and dust. Over time, collisions between these small objects can create new debris, leading to the formation of debris disks around the star. These disks can have a significant impact on the evolution of the system, as they can alter the orbits of planets and moons through gravitational interactions or collisions. In some cases, debris disks may trigger the formation of new planets or moons, while in others, they may lead to the destruction of existing planets through impacts. The role of debris in shaping planetary systems is a reminder that these systems are not isolated. They are constantly influenced by external forces that can dramatically alter their structure and fate. Another mystery that has intrigued scientists is the role of dark matter in the formation and evolution of planetary systems. Dark matter is a mysterious form of matter that does not emit or interact with light, making it invisible to conventional telescopes. However, it is thought to make up the vast majority of the mass in the universe, and its gravitational influence plays a crucial role in the formation of galaxies and galaxy clusters. While dark matter is not directly involved in the formation of planets, its gravitational effects can influence the structure and dynamics of the larger systems in which planetary systems are embedded. For example, the presence of dark matter in a galaxy can affect the distribution of stars and gas, which in turn can influence the formation of planetary systems. The role of dark matter in planetary system formation is still an open question, and it remains one of the many mysteries that scientists are working to unravel. As we explore the fate of planetary systems, we must also consider the potential for interstellar interactions. Over long periods of time, stars can pass close to each other, and these close encounters can have dramatic effects on planetary systems. A passing star can disturb the orbits of planets, potentially ejecting them from the system or altering their orbits in unpredictable ways. In extreme cases, a close encounter with another star could lead to the capture of a planet, creating a new planetary system. These interstellar encounters are rare on human timescales, but over the lifetime of the galaxy, they are likely to play a significant role in shaping the structure of planetary systems. The search for exoplanets has revealed a staggering diversity of planetary systems, each with its own unique formation history and future evolution. Some systems are stable, with planets in circular orbits that are unlikely to change over billions of years. Others are chaotic, with planets in eccentric orbits that could lead to collisions or ejections. The wide range of planetary system architectures observed in the galaxy suggests that there is no single model for planetary system evolution. Instead, each system is shaped by a combination of factors, including the properties of the star, the initial conditions of the protoplanetary disk, and the interactions between planets, debris, and external forces. One of the most exciting recent discoveries in the study of planetary systems is the detection of planets around pulsars, highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation. These planets are thought to have formed after the pulsar's progenitor star went supernova, possibly from the debris left over from the explosion. The existence of planets around such extreme objects raises fascinating questions about the conditions under which planets can form and survive. It also challenges our understanding of planetary system evolution, as these planets are subject to intense radiation and strong magnetic fields that would make them inhospitable to life as we know it. As we look to the future of planetary system research, the next frontier lies in the detailed characterization of exoplanet atmospheres. By studying the composition of exoplanet atmospheres, scientists hope to learn more about the conditions on these distant worlds and their potential to host life. New telescopes and observation techniques, such as the James Webb Space Telescope and ground-based observatories, will allow for unprecedented observations of exoplanet atmospheres, providing insights into the chemical processes that shape planetary environments. These observations will help us understand the diversity of planetary systems and their potential for habitability. The formation and fate of planetary systems is a rich and complex field of study, filled with unanswered questions and tantalizing mysteries. From the initial stages of planet formation to the long-term evolution of planetary orbits and the eventual death of stars, each stage of a planetary system's life offers new challenges and insights into the processes that govern the cosmos. As our understanding of these systems grows, we will continue to uncover the secrets of how planets form, evolve, and ultimately meet their end, deepening our appreciation for the intricate dance of matter and energy that shapes the universe. The ultimate fate of planetary systems is governed by several factors, many of which unfold over timescales far beyond the span of human history. When considering the long-term evolution of these systems, we must account for phenomena that occur on the order of billions, trillions, or even longer spans of time. These processes can lead to the gradual unraveling or transformation of a planetary system, influenced by forces both internal and external. Among the most significant of these forces is the slow, inexorable change that occurs as stars evolve and die, as well as the potential for interstellar and intergalactic events to intervene. A star's life cycle is central to the ultimate fate of the planets that orbit it. As stars exhaust their nuclear fuel, their properties change dramatically, which can have catastrophic effects on their planets. The example of our Sun serves as a model for what will eventually happen to all similar stars in the universe. Over billions of years, the Sun's core will run out of hydrogen, the primary fuel for nuclear fusion. When this happens, the core will contract, while the outer layers expand, transforming the Sun into a red giant. During this phase, the Sun's size will increase enormously, potentially engulfing the inner planets, including Earth. This phase marks the beginning of the end for many planetary systems. In the red giant phase, a star like the Sun sheds much of its outer material into space, forming a planetary nebula. What remains of the star is a dense core, known as a white dwarf. This transition radically alters the environment of the surviving planets. For those that escape being engulfed, the loss of the star's outer layers and the reduced radiation from the white dwarf means the planets will experience extreme changes in their climates. The habitable zones of these systems shrink dramatically, leaving planets frozen and lifeless. The once vibrant system becomes a ghostly remnant, where any surviving planets orbit a dim, cooling white dwarf, devoid of the energy needed to sustain life as we know it. In some cases, planetary systems may survive for a time around these dying stars, but their fates are far from secure. White dwarfs are incredibly dense and have strong gravitational fields, which can alter the orbits of any surviving planets or debris. Over time, gravitational interactions between planets or other bodies in the system can lead to instabilities. These instabilities might cause planets to be ejected from the system entirely, leaving them to drift through interstellar space as rogue planets. Alternatively, planets may collide with one another, or with the central white dwarf, in catastrophic impacts. These gravitational dynamics can be particularly unpredictable in binary or multiple star systems, where the presence of more than one star can introduce complex and chaotic gravitational influences. In such systems, planets may find themselves in unstable orbits, leading to dramatic shifts over time. For example, the gravitational tug-of-war between two stars may eject planets into interstellar space or send them spiraling into one of the stars. This chaotic behavior makes predicting the long-term evolution of planetary systems and binary star systems particularly challenging, and it suggests that many such systems may be more volatile than previously thought. Beyond the immediate influence of the star and planets, planetary systems are also vulnerable to external forces. Over the course of millions or billions of years, stars within a galaxy can pass relatively close to one another. During these close encounters, the gravitational influence of a passing star can perturb the orbits of planets in the system, leading to significant changes. In some cases, a planet may be flung out of the system entirely, becoming a rogue planet, while in others, the gravitational disturbance may destabilize the system, leading to collisions or other catastrophic events. These encounters are rare on human timescales, but over the life of the galaxy, they can play a significant role in shaping the fates of planetary systems. One of the most intriguing possibilities for the future of planetary systems is the potential for planets to become rogue planets, drifting through the interstellar medium without a parent star. Rogue planets may be ejected from their systems during the chaotic early stages of planet formation or as a result of gravitational interactions later in the system's life. Once ejected, these planets travel through space, no longer bound to a star. While they are isolated and receive no warmth or light from a host star, rogue planets may still retain internal heat, generated by the processes of their formation or by radioactive decay. Some scientists speculate that rogue planets could harbor life in subsurface oceans, protected from the harshness of space by thick layers of ice or rock. As we consider the distant future of planetary systems, it becomes clear that no system remains static forever. Even after the death of a star, gravitational interactions continue to shape the system's evolution. Over time, these interactions can lead to the eventual dissolution of the system, as planets either ejected or collide with one another. In the most extreme scenarios, entire planetary systems may be disrupted by the tidal forces exerted during close encounters with other stars, leading to the scattering of planets and debris into interstellar space. In the most distant future, planetary systems are subject to the slow, inevitable process of galactic dynamics. As galaxies evolve, their stars and planetary systems are gradually redistributed by gravitational forces. Over trillions of years, stars and their planets may drift away from the galactic center or become part of new galactic structures, such as galaxy mergers or clusters. These processes can dramatically alter the structure of planetary systems, leading to the eventual disruption of even the most stable configurations. In the far future, as galaxies themselves begin to fade, planetary systems may find themselves alone in the vast darkness of a universe that has expanded to the point where even nearby galaxies are no longer visible. The concept of galactic mergers presents another layer of complexity in understanding the fate of planetary systems. Over time, galaxies collide and merge with one another, as evidenced by the upcoming merger between the Milky Way and the Andromeda Galaxy. During such events, the gravitational forces at play can dramatically reshape the structure of planetary systems. While the distances between stars are vast, and direct collisions between stars are rare, the gravitational interactions can lead to significant disruptions. Some planetary systems may survive the merger intact, while others may be ejected into intergalactic space or destroyed by the intense gravitational forces. The result of such mergers is a new galaxy, with a different structure and dynamics, and the fates of the individual planetary systems within it remain uncertain. As we explore these long-term scenarios, we must also consider the potential role of dark energy in shaping the future of planetary systems. Dark energy is the mysterious force that is driving the accelerated expansion of the universe. As the universe continues to expand, galaxies are moving away from each other at an increasing rate. In the distant future, this expansion could lead to the isolation of galaxies, as the space between them expands faster than the speed of light. This would effectively cut off any possibility of interaction between galaxies, leaving planetary systems isolated within their own galaxies. Over time, the expansion of the universe could lead to the dissolution of galaxies themselves, as the gravitational forces that hold them together are overcome by the relentless pull of dark energy. In the most extreme scenario, known as the Big Rip, dark energy could eventually tear apart not only galaxies and planetary systems, but also stars, planets, and even atoms themselves. In this scenario, the universe would continue to expand at an accelerating rate until the very fabric of space-time is torn apart. While this is a speculative and highly debated hypothesis, it highlights the profound uncertainty that surrounds the ultimate fate of planetary systems and the universe as a whole. The mysteries of planetary system formation and evolution are deeply intertwined with the broader mysteries of the cosmos. From the chaotic early stages of planet formation to the long-term dynamics of gravitational interactions, the life cycle of a planetary system is a complex and ever-changing process. As we continue to study these systems, we gain new insights into the forces that shape the universe and the potential for life to exist beyond our own solar system. But for all that we have learned, many questions remain unanswered. How common are Earth-like planets in the galaxy? What conditions are necessary for life to emerge and thrive on these planets? And what will ultimately happen to our own solar system as the Sun reaches the end of its life? These questions drive the search for exoplanets and the study of planetary systems across the galaxy. With new telescopes and observation techniques, we are poised to make groundbreaking discoveries in the coming decades. As we continue to explore the vastness of space, we may find answers to some of the most profound questions about the formation and fate of planetary systems, and perhaps even our own place in the universe. The search for answers to the mysteries of planetary system formation and evolution continues to drive scientific inquiry. Technological advancements, such as the development of powerful telescopes and space-based observatories, have expanded our ability to observe and study distant exoplanets and their systems in unprecedented detail. Through these observations, we have come to realize that planetary systems are incredibly diverse, with a variety of configurations and outcomes that challenge our preconceptions. One of the most exciting recent developments in this field is the discovery of exoplanets, planets that orbit stars outside our solar system. Since the first confirmed detection of an exoplanet in 1992, thousands of these distant worlds have been discovered, revealing a vast range of planetary types and system architectures. Some exoplanets are small, rocky worlds like Earth, while others are gas giants many times the size of Jupiter. Some orbit their stars at blisteringly close distances, completing a full orbit in just a few days, while others are located in distant, cold regions far from their parent stars. This diversity challenges our understanding of how planetary systems form and evolve and suggests that our solar system may not be the typical model we once thought it was. A key tool in the study of exoplanets is the transit method, which involves detecting the tiny dip in a star's brightness as a planet passes in front of it. This method has been particularly successful in identifying Earth-sized planets in the habitable zones of their stars, where conditions might be right for liquid water to exist, a crucial factor for the potential development of life. The Kepler Space Telescope, launched in 2009, played a central role in revolutionizing our understanding of exoplanets by discovering thousands of these worlds using the transit method. More recently, the Transiting Exoplanet Survey Satellite, TESS, has continued this mission, identifying even more exoplanets and helping to refine our models of planetary system formation. Another method used to detect exoplanets is radial velocity, which measures the wobble of a star caused by the gravitational pull of an orbiting planet. This technique has been instrumental in detecting massive gas giants and planets that orbit farther from their stars. Combined with the transit method, radial velocity helps us determine the mass and size of exoplanets, providing a clearer picture of their composition and potential habitability. As we discover more exoplanets, we are beginning to recognize patterns in planetary system formation. For example, many systems appear to contain hot Jupiters, gas giants that orbit very close to their stars. These planets defy traditional models of planet formation, which suggests that gas giants should form far from their stars, where icy materials are more abundant. The existence of hot Jupiters suggests that these planets formed farther out in their systems and then migrated inward, possibly due to interactions with other planets, or the protoplanetary disk from which they formed. This migration process may also explain why some systems appear to lack smaller, rocky planets like Earth. The discovery of exoplanetary systems with multiple planets has further complicated our understanding of planetary system formation. Some of these systems contain planets in tightly packed orbits, with multiple planets orbiting closer to their star than Mercury does to the Sun. Others feature widely spaced planets in eccentric orbits. These diverse configurations suggest that planetary system formation is a chaotic process, influenced by a variety of factors, including the mass and composition of the protoplanetary disk, gravitational interactions between planets, and the influence of nearby stars. One particularly intriguing finding is the discovery of super-Earths, planets larger than Earth but smaller than Neptune. These planets are common in other planetary systems but are absent from our own solar system, raising questions about why our system lacks this type of planet. Some theories suggest that Jupiter's early migration through the solar system may have disrupted the formation of super-Earths, while others propose that our protoplanetary disk simply didn't have the right conditions to form them. The study of exoplanets has also led to the discovery of planets in the habitable zones of their stars, where conditions might be right for life to exist. These planets, often referred to as potentially habitable exoplanets, are the focus of intense scientific interest. The search for life beyond Earth is one of the driving forces behind the study of exoplanets, and the discovery of habitable zone planets offers tantalizing clues about the possibility of life elsewhere in the universe. However, simply being in the habitable zone does not guarantee that a planet is suitable for life. Many other factors, such as the planet's atmosphere, magnetic field, and geologic activity, play crucial roles in determining its habitability. As we continue to study exoplanets and their systems, we are also learning more about the various stages of planetary system evolution. The chaotic early stages of planet formation often lead to violent collisions between protoplanets, which can result in the formation of moons, such as Earth's own moon, which is believed to have formed from a collision between a Mars-sized body and the young Earth. Over time, as planets settle into stable orbits, their atmospheres and surfaces evolve, shaped by processes such as volcanic activity, asteroid impacts, and interactions with their parent stars. In some cases, planets may undergo dramatic changes as a result of interactions with other planets or external forces. For example, tidal forces from a nearby star can cause a planet to become tidally locked, with one side permanently facing the star and the other side in perpetual darkness. This phenomenon can lead to extreme temperature differences between the two sides of the planet, with one side scorching hot and the other frozen. Tidal forces can also lead to intense volcanic activity, as is the case with Jupiter's moon Io, which experiences constant volcanic eruptions due to the gravitational pull of Jupiter and its other moons. The study of planetary systems also raises intriguing questions about the potential for planets to harbor life in environments that are very different from Earth's. For example, some scientists have proposed that life might exist on icy moons with subsurface oceans, such as Jupiter's moon Europa or Saturn's moon Enceladus. These moons are far from the Sun and receive little warmth, but they may have internal heat sources that could support life in their underground oceans. The discovery of life in such environments would have profound implications for our understanding of the conditions necessary for life and the potential for life to exist elsewhere in the universe. The search for extraterrestrial life also extends to the atmospheres of exoplanets. Scientists are developing techniques to analyze the atmospheres of distant planets by studying the light that passes through them during transits. This technique, known as transmission spectroscopy, allows researchers to identify the chemical composition of a planet's atmosphere and search for potential biosignatures, indicators of life, such as oxygen or methane. The discovery of a planet with an atmosphere rich in these biosignatures would be a major breakthrough in the search for life beyond Earth. However, the detection of biosignatures is not straightforward. Many processes can produce the same chemical compounds that life does, so scientists must be careful to rule out non-biological explanations. For example, methane can be produced by volcanic activity or hydrothermal vents, as well as by biological organisms. The detection of multiple biosignatures, combined with other evidence, would strengthen the case for the presence of life on a distant planet. As we look to the future of planetary system studies, the development of next-generation telescopes promises to revolutionize our understanding of these systems. The James Webb Space Telescope, JWST, launched in 2021, is designed to observe exoplanets in greater detail than ever before, providing new insights into their atmospheres, compositions, and potential habitability. Other upcoming missions, such as the European Space Agency's Plato mission and NASA's HabEx and LUVOIR concepts, aim to directly image Earth-like exoplanets and study their atmospheres for signs of life. These advancements in observational technology, combined with new theoretical models, are likely to lead to groundbreaking discoveries in the coming decades. As we continue to explore the diversity of planetary systems in our galaxy, we may find that our own solar system is just one example of many possible outcomes of planet formation. We may also discover that planets capable of supporting life are more common than we once thought, raising the tantalizing possibility that we are not alone in the universe. The study of planetary systems is a field that is constantly evolving, driven by new discoveries and technological advancements. From the chaotic early stages of planet formation to the ultimate fate of planets orbiting dying stars, the life cycle of planetary systems is shaped by a complex interplay of forces. As we continue to explore the mysteries of planetary system formation and evolution, we are likely to uncover new insights into the nature of the universe and the potential for life beyond Earth. The fate of planetary systems is as intriguing as their formation. Just as planetary systems emerge from the remnants of stars and dust, they also experience a life cycle that inevitably leads to their eventual demise. The end stages of a planetary system are dictated by the fate of its host star, which influences the destiny of the planets, moons, and other objects that orbit it. To understand the future of planetary systems, we must first examine the life cycles of stars and how they affect the planets around them. Stars, the central figures in planetary systems, live out their lives on timescales that vary depending on their mass. The most massive stars burn through their nuclear fuel at an accelerated rate, living for only a few million years, while smaller stars, like red dwarfs, can burn steadily for trillions of years. Our Sun, a middle-aged star, is expected to live for about 10 billion years in total, with roughly 5 billion years remaining before it exhausts its nuclear fuel. When a star like the Sun reaches the end of its life, it will enter a phase known as the red giant stage. During this phase, the star expands dramatically, engulfing any nearby planets. In our solar system, this process will likely consume the inner planets, including Mercury and Venus. Earth may survive this engulfment, but its fate is uncertain. If it is not swallowed by the expanding Sun, it will experience extreme heating as the Sun's outer layers approach, causing the oceans to boil away and the surface to become uninhabitable. Eventually, the Sun will shed its outer layers, creating a glowing shell of gas called a planetary nebula, leaving behind a dense core known as a white dwarf. A white dwarf is the remnant of a star that has exhausted its nuclear fuel. It is incredibly dense, with a mass comparable to the Sun but a size similar to that of Earth. While white dwarfs no longer produce energy through nuclear fusion, they can still emit heat and light for billions of years as they gradually cool. Any surviving planets in the system will continue to orbit the white dwarf, although their orbits may have shifted due to the loss of mass from the dying star. Planets that remain in orbit around a white dwarf may face a variety of fates. Some may become frozen, barren worlds as their heat sources are extinguished. Others may experience gravitational perturbations from neighboring planets or nearby stars, causing their orbits to become unstable. In some cases, planets may be ejected from the system entirely, becoming rogue planets that drift through interstellar space without a host star. These rogue planets represent another fascinating mystery in planetary science. Without the light and heat of a star, these planets could potentially harbor life in extreme conditions, particularly if they have internal heat sources such as geothermal activity. While white dwarfs represent the end stage of stars like our Sun, more massive stars experience a much more violent demise. When a massive star exhausts its nuclear fuel, it undergoes a supernova, a powerful explosion that can outshine an entire galaxy for a brief period. The supernova blasts the outer layers of the star into space, leaving behind either a neutron star or a black hole, depending on the mass of the star's core. Neutron stars are incredibly dense objects, composed almost entirely of neutrons, with a radius of only about 10 kilometers but a mass greater than that of the Sun. Their immense gravity can cause any nearby planets to be torn apart or flung out of the system. Some neutron stars emit powerful beams of radiation, becoming pulsars, spinning neutron stars that emit regular pulses of light. Planets that orbit pulsars experience extreme radiation levels, making them unlikely candidates for habitability. But the discovery of pulsar planets orbiting neutron stars, has shown that planetary systems can survive even the most violent stellar deaths. The most extreme outcome of stellar death is the formation of a black hole, which occurs when the core of a massive star collapses under its own gravity to a point of infinite density. Black holes exert such strong gravitational forces that not even light can escape from them. While black holes are often associated with destruction, it is possible for planets to orbit them in stable orbits, as long as they are far enough away to avoid being pulled into the event horizon. These planets would be subjected to extreme tidal forces, and any life that developed on them would have to contend with the intense gravitational environment. The study of planetary systems around stellar remnants, such as white dwarfs, neutron stars, and black holes, is still in its early stages, but it holds the potential to answer fundamental questions about the resilience of planets and the conditions under which they might survive extreme environments. In some cases, planetary systems may even form around stellar remnants. For example, debris left over from the death of a star can coalesce into a disk, similar to the protoplanetary disks from which planets form around young stars. Over time, this debris could give rise to new planets, leading to the formation of a second-generation planetary system. As we consider the long-term fate of planetary systems, we must also take into account the larger-scale processes that occur in the universe. Galaxies are not static objects. They are constantly evolving and interacting with one another. The Milky Way, for example, is on a collision course with the Andromeda Galaxy, which is expected to occur in about 4 billion years. When galaxies collide, their stars and planetary systems can be disrupted, potentially leading to the ejection of planets from their systems or the destruction of planets through gravitational interactions. The ultimate fate of the universe itself is another factor that will determine the long-term future of planetary systems. Current cosmological models suggest that the universe is expanding at an accelerating rate, driven by a mysterious force known as dark energy. If this expansion continues indefinitely, the universe may experience a heat death, in which all stars burn out and galaxies drift apart, leaving only isolated remnants of planetary systems. In this scenario, planets that survive the deaths of their stars would eventually become cold, lifeless worlds, drifting through an increasingly empty and dark universe. Another possible fate of the universe is the Big Rip, in which the accelerating expansion eventually tears apart galaxies, stars, and even atoms. In this scenario, planetary systems would be destroyed long before the final moments of the universe. Alternatively, the universe could experience a Big Crunch, in which the expansion reverses and everything collapses back into a singularity. This would mark the end of all planetary systems as we know them, but some theories suggest that the universe could undergo a cyclic process of expansion and contraction, with new planetary systems forming in the aftermath of each Big Bang. These cosmic-scale processes remind us that planetary systems, like all structures in the universe, are temporary. While the formation of planets and their systems is a fascinating and complex process, their eventual demise is equally inevitable. The study of these processes helps us to better understand the life cycles of stars, the nature of the universe, and the potential for life beyond Earth. As we continue to explore the mysteries of planetary systems, we are likely to encounter new surprises and challenges to our current understanding. The diversity of planetary systems, the resilience of planets in extreme environments, and the potential for life in unexpected places all point to a universe that is far more complex and dynamic than we ever imagined. By studying the formation and fate of planetary systems, we not only learn more about the universe around us, but we also gain insight into our own place within it, our origins, our future, and the possibilities for life beyond our home planet. The mysteries surrounding the fate of planetary systems are not just confined to their individual stars or the broader cosmic fate of the universe. Other intriguing processes play a role in shaping the evolution and eventual end of these systems, many of which challenge the traditional understanding of planetary stability. One such factor is the migration of planets within their solar systems. Planetary migration, a process where planets shift from their original orbits, can have dramatic and unpredictable consequences on the structure of the planetary system as a whole. In the early stages of planetary system formation, migrating planets can shape the final arrangement of the system. For example, gas giants like Jupiter are believed to have migrated during the early formation of our solar system, moving closer to and then further away from the Sun. This movement would have had a significant impact on the formation and orbital stability of the smaller, rocky planets like Earth. It is thought that these gas giants' movements could have even prevented the formation of other planets in certain regions, such as the asteroid belt between Mars and Jupiter, where the gravitational influence of the gas giant halted planetary accretion. While migration typically occurs in the early stages of a planetary system's life, it can also happen much later, driven by gravitational interactions between planets, nearby stars, or passing objects. The long-term gravitational dance of planets can lead to changes in their orbits over billions of years. These shifts can cause planets to either move toward or away from their host stars, or even lead to planetary collisions or ejections from the system altogether. The possibility that planets could be ejected from their systems introduces another compelling mystery: the existence of rogue planets, wandering through interstellar space without a parent star. Rogue planets, or free-floating planets, represent one of the most fascinating and poorly understood phenomena in planetary science. These planets may have formed in the chaotic early stages of a planetary system's development, only to be flung into space by gravitational forces. Alternatively, some rogue planets may have formed on their own in interstellar space, through processes similar to those that give rise to brown dwarfs, objects that straddle the line between planets and stars. Recent observations have suggested that rogue planets may be far more common than previously thought, with potentially billions of these lonely wanderers drifting through our galaxy. Without the warmth and light of a host star, rogue planets exist in extreme conditions. However, some could retain internal heat through geothermal processes or the decay of radioactive elements, potentially creating subsurface oceans where life might exist. The discovery of rogue planets with these characteristics would fundamentally alter our understanding of where and how life can emerge in the universe. It would expand the notion of habitable environments beyond the traditional habitable zone around stars, opening the door to a new realm of possibilities for extraterrestrial life. As rogue planets drift through space, they may occasionally encounter other stars or planetary systems. Such encounters can have dramatic consequences, as the gravitational forces of the rogue planet can perturb the orbits of existing planets, leading to chaos in the system. In some cases, rogue planets could be captured by another star, becoming part of a new planetary system. Alternatively, a close encounter with a star could lead to the destruction of the rogue planet or trigger a collision with other planets or objects in the system. The study of these interactions provides key insights into the dynamic nature of planetary systems and the surprising ways in which they can evolve over time. In addition to rogue planets, the outer regions of many planetary systems contain another mysterious population of objects, icy bodies and comets. In our solar system, the Kuiper Belt and the Oort cloud are home to trillions of icy bodies, remnants of the early stages of planetary formation. These distant regions of the solar system remain largely unexplored, but they hold clues to the history and evolution of our planetary system. Comets, in particular, provide a unique window into the past. These icy bodies originate from the cold, distant regions of the solar system, and are thought to be composed of the primordial material that formed the planets. When a comet is perturbed by the gravitational influence of a planet or nearby star, it can be flung into the inner solar system, where the heat of the sun causes its icy surface to vaporize, creating the characteristic glowing coma and tail. By studying the composition of comets, scientists can gain insights into the conditions that existed in the early solar system, long before the planets formed. Some theories suggest that comets played a key role in the development of life on Earth by delivering water and organic molecules to the early planet. If this is the case, comets could also be important agents in the spread of life throughout the galaxy, carrying the building blocks of life to other planets and moons. This idea, known as panspermia, posits that life could potentially spread from one planetary system to another, hitching a ride on comets, asteroids, or even rogue planets. The long-term behavior of comets and other icy bodies in planetary systems is closely tied to the fate of the host star. As a star evolves and enters its red giant phase, it can eject material that interacts with the outer regions of the system, potentially triggering a surge of cometary activity. In some cases, the gravitational perturbations caused by the dying star may cause comets to be flung inward, impacting planets or moons and delivering fresh material. Such impacts could potentially create new environments for life, or alternatively, cause mass extinctions by triggering catastrophic events. The interactions between comets, asteroids, and planetary systems raise another fundamental mystery: the role of impacts in shaping the evolution of planets and life. Throughout Earth's history, impacts from asteroids and comets have played a crucial role in shaping the planet's surface and its biological history. The impact that led to the extinction of the dinosaurs 65 million years ago is one of the most famous examples, but smaller impacts have also had significant effects on the planet's climate and geology. The discovery of impact craters on other planets and moons throughout the solar system has revealed that these events are common, occurring on timescales of millions to billions of years. The study of impact craters can provide insights into the history of the solar system, the frequency of impacts, and the potential threat that asteroids and comets pose to life on Earth. One of the most significant mysteries related to planetary impacts is the potential for life to be wiped out by a large-scale impact event. While the likelihood of such an event occurring in the near future is low, it remains a possibility that scientists take seriously. Efforts to track and monitor near-Earth objects, NEOs, are underway, with the goal of identifying potential threats and developing strategies to mitigate them. However, the sheer number of objects in the solar system, combined with the unpredictability of their orbits, makes it difficult to predict when and where the next major impact might occur. In addition to the threats posed by comets and asteroids, planetary systems also face potential dangers from more exotic sources, such as gamma-ray bursts and supernovae. Gamma-ray bursts are the most powerful explosions in the universe, releasing more energy in a few seconds than the Sun will emit over its entire lifetime. If a gamma ray burst were to occur within a few thousand light-years of Earth, the intense radiation could strip away the planet's atmosphere, causing a mass extinction event. Supernovae, the explosive deaths of massive stars, pose a similar threat. While supernovae are relatively rare, occurring only once every few centuries in a galaxy the size of the Milky Way, their effects can be devastating to nearby planetary systems. The shockwave from a supernova can strip away the atmospheres of planets, sterilize their surfaces, and even alter their orbits. The potential for supernovae and gamma-ray bursts to disrupt planetary systems is a stark reminder of the fragility of life in the universe, and the many ways in which it can be extinguished. These cosmic threats highlight the interconnectedness of planetary systems and the broader universe. Planetary systems do not exist in isolation. They are part of a dynamic and ever-changing cosmic environment, influenced by the movements and interactions of stars, galaxies, and other objects on both small and large scales. Understanding the fate of planetary systems requires not only a detailed knowledge of their internal dynamics, but also an appreciation for the external forces that shape their evolution. As astronomers continue to explore the universe, they are uncovering new and unexpected mysteries about planetary systems. From the discovery of rogue planets and pulsar planets to the study of planetary migration and the effects of cosmic impacts, each new discovery challenges our understanding of the universe and opens up new possibilities for exploration and discovery. The fate of planetary systems is a story that is still being written, with many questions remaining unanswered. How do planets survive the death of their stars? Can life exist in extreme environments like rogue planets or pulsar systems? What role do comets and asteroids play in the development of life? And how can we protect our own planet from the threats they pose? These are just some of the mysteries that continue to intrigue scientists and inspire further exploration. As we delve deeper into the fate of planetary systems, one aspect that often emerges is the role of planetary atmospheres and the intricate balance required to sustain them. The evolution of a planet's atmosphere can be influenced by its proximity to its host star, its magnetic field, and external cosmic events such as supernovae or gamma-ray bursts. Over billions of years, atmospheres can evolve dramatically, often determining the ultimate habitability of the planet. Understanding how atmospheres form, evolve, and eventually dissipate is crucial to understanding the fate of not just individual planets, but the systems they inhabit. For planets located in the habitable zone, the region around a star where liquid water can exist, an atmosphere acts as a shield, protecting the surface from harmful radiation and creating the conditions necessary for life. Earth, for example, owes much of its habitability to its atmosphere, which regulates temperature, provides essential gases for life, and shields the surface from cosmic radiation. However, maintaining this delicate balance over geological timescales is no simple feat, and the atmosphere can be vulnerable to both internal and external factors. One of the primary threats to planetary atmospheres is the activity of their host star. Young stars, in particular, can emit powerful solar winds and flares, stripping away the atmospheres of nearby planets. This process, known as atmospheric escape, is thought to have played a major role in the early history of Mars. Billions of years ago, Mars likely had a thick atmosphere and liquid water on its surface, but over time, the solar wind from the young sun stripped away much of its atmosphere, leaving the planet cold, dry, and barren. Today, Mars' atmosphere is a thin shell of its former self, offering little protection from cosmic radiation. Atmospheric escape can be even more extreme in planetary systems with high levels of stellar activity. For planets orbiting close to their host stars, such as many of the hot Jupiters discovered in other systems, the intense radiation and solar wind can strip away the atmosphere entirely, leaving the planet exposed. In some cases, this process can be so extreme that the planet's atmosphere is literally blown into space, creating a tail of gas that trails behind it, much like a comet. Observations of these evaporating planets provide a dramatic example of the dynamic interactions between planets and their stars, and highlight the fragility of planetary atmospheres in the face of stellar forces. The fate of a planet's atmosphere is also influenced by its magnetic field. Earth, for example, is protected by its magnetic field, which deflects charged particles from the solar wind and prevents them from stripping away the atmosphere. Without this magnetic shield, Earth's atmosphere would likely suffer the same fate as Mars. However, not all planets have strong magnetic fields, and the reasons for this are still not fully understood. A planet's magnetic field is generated by the movement of molten metal in its core, and the conditions necessary for sustaining this process over long periods of time may be more rare than we realize. The loss of a planet's magnetic field can have catastrophic consequences. Mars, for instance, may have once had a magnetic field, but as its core cooled and solidified, the magnetic field weakened and eventually disappeared. Without this protective shield, the solar wind was able to strip away much of Mars' atmosphere, transforming it from a potentially habitable world to the desolate planet we see today. The study of planetary magnetic fields is a growing field in astronomy, as scientists seek to understand how these fields are generated, how long they last, and what role they play in the long-term habitability of planets. In addition to solar winds and magnetic fields, a planet's atmosphere can be influenced by the impacts of asteroids and comets. Large impacts can blast away significant portions of a planet's atmosphere, especially in the early stages of a system's formation when impacts are more frequent. Some theories suggest that the early atmospheres of Earth and other planets may have been heavily modified by these impacts, with material being ejected into space and new gases being introduced into the atmosphere as a result of the collisions. However, impacts are not always destructive. Some scientists believe that comets and asteroids could have played a key role in delivering water and other volatile compounds to Earth, helping to build up the planet's atmosphere and oceans. This idea, known as the late heavy bombardment, suggests that during a period of intense comet and asteroid activity, the inner planets of the solar system were bombarded with icy bodies that delivered the water necessary to form Earth's oceans. If this is the case, then the very same impacts that could have stripped away atmospheres may also have been responsible for creating the conditions necessary for life. The interactions between planetary atmospheres, impacts, and stellar activity highlight the complexity and fragility of planetary systems. A planet's atmosphere is not a static entity, but rather a dynamic system that can change dramatically over time in response to internal and external forces. Understanding how these forces interact is key to understanding the long-term evolution of planetary systems, and the potential for habitability on planets both within and beyond our solar system. As we look to the future, the search for habitable exoplanets, planets outside our solar system, continues to be one of the most exciting and rapidly developing areas of astronomy. With thousands of exoplanets already discovered, scientists are now focused on identifying those that might have conditions similar to Earth, with stable atmospheres, liquid water, and the potential for life. This search is complicated by the many factors that can influence a planet's habitability, from its distance from its star to the presence of a magnetic field and the stability of its atmosphere. The discovery of exoplanets in the habitable zones of their stars has fueled speculation about the possibility of life elsewhere in the universe. Some of these planets, such as those found orbiting red dwarf stars, are located in regions where liquid water could exist on the surface, making them prime candidates for further study. However, red dwarfs are known for their high levels of stellar activity, which could make it difficult for planets in these systems to maintain stable atmospheres. The question of whether life could survive in such environments remains one of the great mysteries of planetary science. In addition to the search for habitable planets, scientists are also exploring the possibility that life could exist in more extreme environments, such as the subsurface oceans of icy moons like Europa and Enceladus. These moons, which orbit Jupiter and Saturn respectively, are believed to harbor liquid water beneath their icy surfaces, kept warm by the gravitational forces of their parent planets. The discovery of water plumes erupting from Enceladus suggests that these subsurface oceans may be connected to the surface, raising the possibility that life could exist in these hidden environments. The study of these icy moons has opened up new possibilities for understanding the conditions under which life might arise. If life can exist in the dark, cold oceans of Europa or Enceladus, far from the warmth of the sun, then it raises the question of whether similar environments might exist elsewhere in the galaxy. Could rogue planets, with internal heat sources, harbor subsurface oceans where life might thrive? Could icy bodies and other planetary systems hold the key to understanding the potential for life beyond Earth? The exploration of these questions is still in its early stages, but the discovery of life in such environments would have profound implications for our understanding of the universe. It would suggest that life is not confined to the narrow range of conditions found on Earth, but can exist in a much wider variety of environments than previously thought. This, in turn, would increase the likelihood that life exists elsewhere in the galaxy, perhaps even in places we have yet to imagine. The fate of planetary systems, then, is not just a matter of the physical processes that shape planets and stars, but also of the biological possibilities that arise within these systems. As we continue to explore the universe, we are likely to encounter new and unexpected mysteries that challenge our understanding of planetary evolution, habitability, and the potential for life. Each new discovery adds another piece to the puzzle, bringing us closer to understanding the full complexity of the universe and our place within it. As we continue to explore the mystery surrounding the formation and fate of planetary systems, it becomes evident that the dynamics governing these systems are deeply interconnected. One of the most significant challenges in understanding planetary evolution is the role that giant planets play in shaping the architecture of their systems. In our solar system, Jupiter and Saturn are the dominant gravitational forces beyond the asteroid belt, and their influence extends far beyond their orbits. The gravitational pull of these gas giants has profound effects on the distribution of smaller bodies, the migration of planets, and the potential for habitable worlds. Jupiter, in particular, has been referred to as the protector of the inner solar system due to its ability to deflect or capture incoming comets and asteroids that might otherwise pose a threat to Earth. Its immense gravity acts as a shield, redirecting objects that could impact the inner planets. However, this protective role is not absolute. There is evidence to suggest that Jupiter's gravity may have also directed some objects toward the inner solar system, leading to periods of intense bombardment, such as the late heavy bombardment mentioned earlier. This dual role as both a protector and a potential instigator of impacts highlights the complex and sometimes contradictory nature of planetary interactions. The presence of giant planets and other planetary systems raises similar questions. Many of the first exoplanets discovered were hot Jupiters, gas giants that orbit extremely close to their host stars. These planets, which are much larger than Earth, orbit within a fraction of the distance between the Earth and the Sun, completing their orbits in just a few days. Their discovery challenged existing theories of planetary formation, which predicted that gas giants should form far from their stars, where temperatures are cool enough for gas to condense. The existence of hot Jupiter suggests that planetary migration, where planets move inward or outward from their original orbits, is a common occurrence in planetary systems. The migration of giant planets can have dramatic consequences for the other planets in a system. As a gas giant moves inward, it can destabilize the orbits of smaller, rocky planets, ejecting them from the system or sending them crashing into the star. This process, known as planetary scattering, can drastically alter the architecture of a planetary system, and may explain why many exoplanet systems look very different from our own. In some cases, the inward migration of a gas giant can lead to the formation of tightly packed planetary systems, where multiple planets orbit close to their star in a stable configuration. In other cases, the migration can result in chaotic systems with highly eccentric orbits and frequent collisions. The discovery of planetary migration has also led scientists to reconsider the early history of our own solar system. There is evidence to suggest that both Jupiter and Saturn may have migrated inward during the early stages of the solar system's formation, before settling into their current orbits. This migration would have had significant implications for the formation of the terrestrial planets, as the movement of the gas giants could have disrupted the disk of gas and dust from which the planets were forming. Some models suggest that Jupiter's inward migration may have prevented the formation of a super-Earth in the inner solar system, a type of planet that is common in other planetary systems but absent from our own. In addition to the role of giant planets, Another important factor in the evolution of planetary systems is the presence of debris disks. These disks, composed of dust, ice, and small rocky bodies, are the remnants of the planet formation process and can provide valuable clues about the history of a system. In our solar system, the Kuiper Belt and the Oort cloud are two such regions, containing billions of icy bodies that were left over from the formation of the planets. These distant regions serve as reservoirs for comets, which occasionally make their way into the inner solar system. Debris disks are not unique to our solar system. Observations of other stars have revealed the presence of similar disks, often glowing in infrared light as the dust and ice reflect the heat of the star. The structure of these disks can provide important information about the planets in the system. For example, gaps in the disk may indicate the presence of planets that have cleared out the material in their orbits. In some cases, the gravitational influence of a planet can create spiral patterns or rings in the disk, similar to the structures seen in Saturn's rings. The study of debris disks has also revealed that planetary systems can be highly dynamic, with collisions between planets and smaller bodies continuing long after the initial formation of the system. In some systems, astronomers have observed evidence of ongoing collisions between large planetesimals, the building blocks of planets. These collisions can generate vast amounts of dust, which can be detected by telescopes as a bright disk around the star. Such observations suggest that planet formation is not a neat and orderly process, but rather a violent and chaotic one, with planets continuing to collide and interact long after their initial formation. The fate of planetary systems is not limited to the interactions between planets and debris disks. The long-term evolution of a system is also shaped by the gradual aging of its star. As stars like the Sun age, they go through a series of changes that can have dramatic effects on the planets in their orbits. Over billions of years, a star's luminosity increases as it exhausts its hydrogen fuel and begins to burn helium. For planets in the habitable zone, this increase in brightness can lead to a runaway greenhouse effect, as happened on Venus, where the planet's atmosphere traps heat and causes surface temperatures to rise to extreme levels. As the star continues to evolve, it eventually enters the red giant phase, expanding to many times its original size. For planets close to the star, this expansion can be catastrophic. Mercury and Venus, for example, are expected to be engulfed by the Sun when it becomes a red giant, their surfaces vaporized by the intense heat. Earth may or may not survive this phase, depending on the extent of the Sun's expansion, but even if it avoids being engulfed, the conditions on the planet will be inhospitable. The oceans will evaporate, the atmosphere will be stripped away, and the surface will be scorched by the dying sun. Eventually, the star will shed its outer layers, leaving behind a dense core known as a white dwarf. This small, dim object will slowly cool over billions of years, fading into obscurity. For any remaining planets, the end of their host star marks the end of their evolution. Without the heat and light of the star, the planets will become cold, frozen worlds, drifting through space in the twilight of their system. However, not all planetary systems meet such a quiet end. In some cases, the death of a star can trigger a new phase of activity. When a massive star reaches the end of its life, it explodes in a supernova, sending shockwaves and heavy elements racing through space. These violent events can disrupt nearby planetary systems, stripping planets of their atmospheres or ejecting them from their orbits. In some cases, the shockwaves from a supernova can trigger the formation of new stars and planets, recycling the material from the dead star into a new generation of planetary systems. The long-term fate of planetary systems is also influenced by interactions with other stars. Stars are not isolated objects. They are often part of larger groups known as star clusters, which can contain hundreds or thousands of stars. Over time, the gravitational interactions between stars in a cluster can alter the orbits of planets, leading to close encounters that can eject planets from their systems or send them spiraling into their host stars. These interactions can also lead to the capture of rogue planets, planets that have been ejected from their original systems and now drift through space without a host star. Rogue planets represent one of the most intriguing mysteries of planetary science. These planets, which may outnumber stars in the galaxy, are difficult to detect because they do not emit light and are not bound to a star. However, gravitational microlensing, where a rogue planet passes in front of a distant star and bends its light, has revealed the existence of these wandering worlds. The conditions on rogue planets are likely extreme, with no sunlight to warm their surfaces, but some scientists speculate that life could still exist on these planets, sustained by internal heat from radioactive decay or tidal forces. The discovery of rogue planets has expanded our understanding of planetary systems and raised new questions about the nature of planet formation and evolution. How do these planets form? Are they ejected from their original systems, or do they form in isolation? What role do they play in the broader galactic environment? As we continue to search for and study these enigmatic objects, we may uncover new insights into the diversity and complexity of planetary systems. As we delve deeper into the mysteries of planetary systems, another crucial aspect emerges: the search for extraterrestrial life. The quest to understand how life might arise on other planets is intricately linked to our knowledge of planetary formation and evolution. The conditions necessary for life, often summarized by the term habitable zone, refer to the region around a star where temperatures are suitable for liquid water to exist. However, defining habitability is more complex than simply identifying the right distance from a star. Beyond just distance, several factors play a role in determining a planet's ability to support life. For instance, a planet's atmosphere is critical in maintaining surface temperatures and protecting potential life forms from harmful radiation. The composition and thickness of an atmosphere can vary significantly depending on a planet's formation history, the presence of a magnetic field, and its proximity to its star. In our own solar system, Earth has a robust atmosphere rich in nitrogen and oxygen, which not only supports life but also stabilizes surface temperatures. In contrast, Venus, despite being in the habitable zone, has a thick atmosphere dominated by carbon dioxide, leading to extreme greenhouse conditions that render it inhospitable. When considering exoplanets, planets outside our solar system, scientists have begun to identify Earth-like candidates that may possess similar characteristics to our home planet. The Kepler Space Telescope, for instance, has discovered thousands of exoplanets, some of which are located in their star's habitable zone. However, determining the true habitability of these planets requires detailed analysis of their atmospheres and surface conditions, often necessitating advanced spectroscopic techniques to identify the presence of water vapor, methane, carbon dioxide, and other potential biosignatures. One of the most promising avenues for exploring habitability is the study of moons within our solar system. Notably, several of the larger moons of gas giants, such as Europa, moon of Jupiter, and Enceladus, moon of Saturn, have garnered interest due to the presence of subsurface oceans beneath their icy crusts. These oceans may provide the right environment for microbial life, insulated from the harsh conditions of space and receiving energy from geothermal vents on the ocean floor. The discovery of plumes of water vapor erupting from Enceladus, for example, has fueled speculation that these moons could host life, potentially offering clues about life's resilience in extreme environments. In addition to the search for life within our solar system, scientists are also investigating the conditions that might allow life to exist around stars very different from our own. For instance, red dwarf stars, which are smaller and cooler than our Sun, are the most common type of star in the galaxy. Many exoplanets have been found orbiting these stars within their habitable zones, but red dwarfs also present challenges for habitability. Their propensity for stellar flares and radiation can create harsh environments for planets, making the study of their potential for supporting life an intriguing area of research. Furthermore, the exploration of exoplanets has raised questions about the potential for life in extreme conditions that challenge our Earth-centric perspective. Some scientists propose that life could thrive in environments that are inhospitable by human standards. For example, extremophiles, organisms on Earth that can survive in extreme heat, cold, pressure, or acidity, suggest that life may be more adaptable than previously thought. This idea expands the scope of our search for life beyond Earth-like conditions, prompting us to consider the possibility of life existing in a variety of environments, including those on gas giants, in the clouds of Venus, or even on rogue planets drifting through the galaxy. As we contemplate the future of planetary systems, we must also consider the implications of human activity on Earth and our responsibility in the broader cosmos. The study of planetary systems has significant implications for understanding climate change and the sustainability of our own planet. By examining how other worlds have evolved, we can gain insights into the long-term consequences of environmental changes, such as shifts in temperature, atmospheric composition, and oceanic conditions. Understanding the delicate balance that allows a planet to sustain life may inform our actions on Earth and highlight the importance of preserving our environment. In this context, the concept of planetary stewardship becomes increasingly relevant. As we develop the technology to explore and potentially colonize other planets, we must also grapple with ethical questions about our role in the universe. The possibility of terraforming, altering a planet's environment to make it more Earth-like, raises profound questions about the rights of extraterrestrial worlds and the potential consequences of such actions. Should we seek to transform other planets, or should we prioritize the preservation of pristine environments? How do we navigate the tension between exploration and exploitation? Additionally, the advancements in our understanding of planetary systems will inform the search for habitable exoplanets and guide the future of space exploration. Initiatives like the James Webb Space Telescope aim to analyze the atmospheres of distant exoplanets, searching for biosignatures that could indicate the presence of life. As we continue to push the boundaries of our technological capabilities, the prospect of discovering extraterrestrial life becomes increasingly tangible, transforming our understanding of our place in the universe. While the mysteries of planetary systems are vast and complex, they also evoke a sense of wonder and curiosity that drives scientific inquiry. Each discovery, whether it's the detection of an exoplanet, the analysis of a distant star's composition, or the exploration of our own solar system's moons, adds a piece to the intricate puzzle of planetary formation and evolution. The interplay between the elements that shape planetary systems, the influence of giant planets, the role of debris disks, the evolution of stars, and the search for life, paints a picture of a dynamic and ever-changing universe. As we peer into the cosmos, we find ourselves not only seeking answers to the questions of our existence, but also grappling with the philosophical implications of our discoveries. The study of planetary systems invites us to consider the nature of life itself, the potential for intelligent civilizations, and the interconnectedness of all celestial bodies. In a universe that is both vast and intimate, we are reminded of our shared heritage as products of the stars, born from the same cosmic processes that shape the worlds around us. The continued exploration of planetary systems will undoubtedly reveal more mysteries, each leading to further questions and deeper understanding. As we stand on the precipice of discovery, we are reminded that the universe is a tapestry woven from the threads of time, space, and matter. The journey to unravel the secrets of planetary formation and fate is far from over, and the stories waiting to be told are as infinite as the stars themselves. Each planet, each moon, and each distant exoplanet holds the promise of discovery, inviting us to embark on an adventure of exploration that transcends the boundaries of our own world. The formation and fate of planetary systems are intricate and multifaceted processes that reflect the broader dynamics of the universe. From the initial formation of stars and their surrounding disks of gas and dust to the complex interactions between planets and their host stars, each stage of evolution offers insights into the nature of celestial bodies and the potential for life beyond Earth. As we continue to explore the cosmos, we find ourselves captivated by the mysteries that lie beyond our reach, motivated by a desire to understand not only where we come from but also where we might be headed in the grand narrative of the universe. As we navigate the complexities of planetary systems, it becomes evident that our understanding of these celestial formations is continually evolving, driven by advances in technology, observational techniques, and theoretical frameworks. A key area of interest in the study of planetary systems is the role of migration, how planets move from their initial formation locations to new orbits, significantly influencing their characteristics and potential for habitability. Planetary migration can occur in several ways, most notably through interactions with the protoplanetary disk from which they form. For example, As a planet forms and grows in size, its gravitational influence can alter the disk structure, creating gaps and spirals that can lead to migration. This process is particularly relevant in the context of giant planets, which can migrate inward toward their star or outward into the colder reaches of the disk. The inward migration of gas giants is a phenomenon observed in many exoplanetary systems, often leading to the formation of hot Jupiters, massive planets that orbit very close to their stars. Hot Jupiters serve as a fascinating case study for understanding planetary dynamics and the implications for potential habitability. Their extreme proximity to their host stars results in intense radiation and high temperatures, rendering them unlikely candidates for supporting life as we know it. However, studying these unusual planets can offer insights into the migration processes that might also affect terrestrial planets in their systems. For instance, understanding how and why gas giants migrate can shed light on the stability of interterrestrial planets and their potential to host life. In addition to migration, the interactions between planets within a system can lead to various outcomes that shape the fate of each body. Gravitational interactions, such as close encounters or resonances, can alter a planet's orbit and influence its climate, geology, and atmospheric conditions. For example, interactions between planets can lead to orbital resonances, where two or more planets exert a regular, periodic gravitational influence on each other. This phenomenon is evident in our own solar system, such as the resonance between Neptune and Pluto, which helps maintain the stability of their orbits. The study of planetary systems also involves understanding the role of smaller bodies, such as asteroids and comets, in shaping the evolution of planets. These bodies can collide with planets, influencing their atmospheres and surface conditions. The Late Heavy Bombardment, a period approximately 4 billion years ago when the inner solar system experienced intense asteroid impacts, is believed to have played a significant role in the geological history of terrestrial planets, including Earth. Such events can disrupt existing ecosystems and potentially deliver the building blocks of life, highlighting the intricate relationships between different celestial bodies within a system. Furthermore, the investigation of exoplanetary systems has revealed a remarkable diversity in their architectures. Some systems contain multiple planets with closely spaced orbits, while others feature wide separations between planets. This variety challenges existing models of planetary formation, prompting scientists to reconsider the processes that govern the creation and arrangement of planetary systems. Observations have shown that the presence of giant planets can significantly influence the distribution and dynamics of smaller, terrestrial planets, affecting their potential for habitability. One of the most profound discoveries in the field of exoplanet studies is the identification of super-Earths, planets larger than Earth but smaller than Neptune. These planets exist in a size range that is not represented in our solar system, leading to questions about their formation, composition, and potential for hosting life. Some super-Earths orbit within their star's habitable zone and possess atmospheres, raising intriguing possibilities for habitability. The conditions on these planets, such as atmospheric pressure and temperature, can significantly differ from those on Earth, prompting scientists to reconsider what constitutes a habitable environment. The fate of planetary systems is also intricately tied to the life cycle of their host stars. As stars age, they undergo significant transformations that can dramatically impact their surrounding planets. For instance, as a star enters the red giant phase, it expands and heats its surrounding environment. This change can have catastrophic effects on any nearby planets, potentially stripping away their atmospheres and altering their surface conditions. In some cases, inner planets may be engulfed entirely, while outer planets may experience changes in their orbits due to the loss of mass from the star. The eventual fate of planetary systems hinges on the ultimate death of their host stars, which can take several forms depending on their mass. Low-mass stars, like our Sun, will evolve into red giants before shedding their outer layers, leaving behind a white dwarf. In contrast, more massive stars may end their lives in spectacular supernova explosions, leaving neutron stars or black holes in their wake. These dramatic events can reshape the surrounding space, affecting nearby planetary systems and potentially leading to the formation of new celestial bodies from the remnants of the exploded star. In contemplating the future of planetary systems, we also confront the notion of cosmic evolution, the idea that the universe itself is in a constant state of change. The formation of new stars and planetary systems is an ongoing process, with regions of space undergoing gravitational collapse to create new celestial bodies. As stars are born, they will inevitably interact with their surroundings, leading to new planetary systems that may resemble or diverge significantly from our own. The study of planetary systems invites us to explore not only the physical processes that shape these worlds, but also the broader implications for understanding life in the universe. As we gather more data on exoplanets, their atmospheres, and their potential for habitability, we are prompted to consider profound questions about our existence. Are we alone in the cosmos, or do other intelligent civilizations exist elsewhere? The search for extraterrestrial life is intricately linked to our exploration of planetary systems, as we seek to understand the conditions that allow life to flourish. As we continue to investigate the mysteries of planetary systems, we find ourselves drawn into a narrative that transcends our individual experience. The cosmos invites us to ponder our place in the universe, to consider the vast timelines of stellar evolution, and to reflect on the interconnectedness of all celestial bodies. Each discovery, whether it be a new exoplanet, a unique planetary formation, or the remnants of a distant star, adds depth to our understanding of the universe and our own origins. In the grand scheme of cosmic history, our solar system is but a fleeting moment, a brief intersection of time and space within a much larger tapestry. The evolution of planetary systems is a testament to the dynamic nature of the universe, where processes of creation and destruction intertwine in a delicate balance. As we gaze into the night sky and contemplate the stars, we are reminded of the countless stories waiting to be uncovered, the mysteries yet to be solved, and the questions that linger in the depths of our curiosity. The journey into the heart of planetary systems is a journey of exploration and discovery, one that connects us to the universe on a fundamental level. Each planet, moon, and star we study offers a glimpse into the forces that shape our reality, revealing the intricate web of relationships that govern the cosmos. The quest for knowledge fuels our desire to understand not only our own world but also the possibilities that lie beyond, as we endeavor to unlock the secrets of the universe and our place within it. As we continue to push the boundaries of our understanding, the mysteries of planetary systems will undoubtedly unfold, leading us to new questions, new discoveries, and new horizons. The allure of the cosmos remains ever present, inviting us to explore the vastness of space and the depths of our imagination. In the grand narrative of the universe, we are not mere observers but active participants in a story that stretches across time and space, shaping the future of planetary systems and the potential for life beyond Earth. Ultimately, the mysteries of the cosmos serve as a reminder of our shared humanity and our innate curiosity. The quest for knowledge, understanding, and exploration transcends, uniting us in a common goal: to seek answers to the questions that have captivated our species for millennia. In this pursuit, we may uncover not only the secrets of planetary systems, but also the fundamental truths about our existence and the nature of the universe itself. As we delve deeper into the formation and fate of planetary systems, it is essential to consider the technological advancements that have revolutionized our understanding of the cosmos. Over the past few decades, telescopes and observational techniques have provided unprecedented insights into the structures and behaviors of distant planetary systems. Space telescopes, such as the Hubble Space Telescope and the Kepler Space Telescope, have enabled astronomers to identify thousands of exoplanets, many of which exhibit characteristics previously thought to be rare or non-existent. The vast array of data collected from these observations has led to significant revisions of our theoretical models regarding planetary formation and dynamics. One of the most groundbreaking techniques employed in exoplanet discovery is the transit method. This approach involves monitoring a star's brightness over time to detect periodic dips in light caused by a planet passing in front of it. The Kepler Space Telescope, launched in 2009, utilized this method to identify thousands of exoplanets, revealing a stunning diversity of planetary systems that challenged previous assumptions about how planets form and interact. The data gathered by Kepler has allowed scientists to analyze the distribution of planetary sizes, orbital periods, and the prevalence of multi-planet systems, offering vital clues about the processes that govern planetary formation. In addition to the transit method, radial velocity measurements have played a crucial role in detecting exoplanets. This technique involves observing the Doppler shift of a star's light caused by the gravitational tug of an orbiting planet. By measuring the changes in the star's spectrum, astronomers can infer the presence of a planet and determine its mass and orbit. The combination of these techniques has provided a comprehensive view of planetary systems and their dynamics, contributing to our understanding of how they evolve over time. As we analyze the data collected from these observations, it becomes clear that planetary systems exhibit a remarkable diversity in their architectures. Some systems are dominated by gas giants orbiting close to their stars, while others feature a plethora of small, rocky planets situated within their habitable zones. This variety raises questions about the underlying processes that lead to such differences in formation and evolution. Scientists have proposed several hypotheses to explain the observed diversity, including variations in the initial conditions of protoplanetary disks, differences in stellar mass and composition, and the impact of nearby stars on the evolution of a planetary system. One intriguing aspect of planetary system formation is the role of instabilities and interactions among multiple planets. Gravitational interactions can lead to significant changes in the orbits of planets, including ejections from the system or inward migrations that bring planets closer to their stars. These processes can lead to the creation of complex orbital resonances, where planets exert periodic gravitational forces on one another, stabilizing their orbits and influencing their long-term dynamics. Observational evidence of such resonances has been found in several exoplanetary systems, suggesting that these interactions are a fundamental aspect of planetary system evolution. Furthermore, the study of young star clusters has provided valuable insights into the early stages of planetary system formation. Observations of these clusters reveal a chaotic environment where gravitational interactions and collisions are common. In such settings, the formation of planets can be highly influenced by the presence of nearby stars, which can gravitationally perturb protoplanetary disks, leading to the formation of different types of planetary systems. This understanding emphasizes the importance of considering the broader context in which planetary systems develop, as their fates may be determined not only by internal dynamics but also by interactions with their stellar neighbors. As we contemplate the fate of planetary systems, it is crucial to address the long-term evolution of their environments. Over time, planets may experience significant changes in their atmospheres and surface conditions due to a variety of factors, including stellar evolution, impacts from asteroids and comets, and geological processes. These changes can influence the potential for habitability, as the conditions necessary for life may be transient rather than permanent. For instance, Mars, once a potentially habitable world with liquid water on its surface, has undergone drastic climatic changes, leading to its current barren state. Understanding the mechanisms driving these transformations is essential for evaluating the potential for life on other planets and the likelihood of finding biosignatures in distant systems. Another key aspect of planetary system evolution is the interplay between stellar activity and planetary atmospheres. As stars age, they undergo changes in their luminosity and activity levels, which can have profound effects on the atmospheres of orbiting planets. For example, young stars often exhibit intense solar flares and high levels of ultraviolet radiation, which can strip away the atmospheres of nearby planets. This process, known as atmospheric escape, can significantly alter a planet's surface conditions and its ability to support life. Conversely, planets located at greater distances from their stars may experience less atmospheric loss, allowing for the retention of water and other essential components for life. The fate of planetary systems is also intricately linked to the eventual death of their host stars. As stars exhaust their nuclear fuel, they undergo dramatic transformations, ultimately leading to their demise. For low-mass stars, like our Sun, this process culminates in the red giant phase, where the outer layers are ejected, creating a planetary nebula, while the core contracts into a white dwarf. In contrast, massive stars end their lives in spectacular supernova explosions, leaving behind neutron stars or black holes. These events not only mark the end of a star's life cycle but can also have far-reaching effects on the surrounding planetary systems. For instance, the intense energy released during a supernova can trigger the formation of new stars from the surrounding gas and dust, contributing to the ongoing cycle of stellar and planetary formation in the universe. Additionally, the materials ejected during a star's death can enrich the interstellar medium, providing the building blocks for future generations of stars and planets. This process highlights the interconnectedness of cosmic evolution, where the fate of one system can influence the birth of others, perpetuating the cycle of creation and destruction throughout the universe. As we reflect on the complexities of planetary systems and their formation and fate, it becomes evident that our understanding is still in its infancy. Each new discovery prompts further questions and challenges existing paradigms, encouraging scientists to refine their models and expand their knowledge. The ongoing exploration of exoplanets and their atmospheres has opened up new avenues for research, particularly in the search for life beyond Earth. The detection of biosignatures, indicators of life, in the atmospheres of distant planets has become a key objective in astrobiology, prompting a reevaluation of what conditions are necessary for life to thrive. In this quest for understanding, the tools at our disposal continue to advance. Next-generation telescopes, such as the James Webb Space Telescope, are set to revolutionize our ability to probe the atmospheres of exoplanets, searching for chemical signatures that may indicate the presence of life. By examining the composition of planetary atmospheres, scientists hope to identify potential biosignatures, such as oxygen, methane, or water vapor, which could suggest the existence of life as we know it. Moreover, the study of extremophiles, organisms that thrive in extreme environments on Earth, has expanded our understanding of the conditions under which life can exist. These resilient life forms challenge traditional notions of habitability, and suggest that life may be able to survive in environments previously thought to be inhospitable. This understanding fuels our curiosity about the potential for life on other planets, particularly in extreme environments, such as the icy moons of Jupiter and Saturn or the surface of Mars. The exploration of planetary systems not only deepens our understanding of the cosmos but also encourages us to contemplate our place within it. The vastness of space, with its myriad of worlds and potential for life, challenges us to reflect on our existence and the unique circumstances that have allowed life to flourish on Earth. As we gaze at the stars, we are reminded of the interconnectedness of all celestial bodies and the shared history that binds us to the universe. The formation and fate of planetary systems is a dynamic and multifaceted subject that continues to captivate our imagination and inspire scientific inquiry. From the processes of planet formation to the intricate interactions that shape their evolution, each aspect reveals the complexities of the cosmos. As we stand on the brink of new discoveries, we are reminded of the endless possibilities that lie ahead in our quest for knowledge. The mysteries of planetary systems beckon us to explore further, to seek answers, and to embrace the unknown, as we endeavor to unravel the secrets of the universe and our place within it. Continuing our exploration of the formation and fate of planetary systems, it's essential to highlight the pivotal role that the chemistry of the universe plays in this grand cosmic narrative. The initial stages of planetary formation are deeply rooted in the elemental building blocks available in the interstellar medium. The elements that comprise the planets, including hydrogen, helium, carbon, oxygen, and metals, originated from ancient stars that produced them through nuclear fusion and subsequently exploded as supernovae, dispersing these materials across the galaxy. When we consider the process of star formation within molecular clouds, we recognize that the density fluctuations within these clouds create regions where gravity can take hold. As these areas collapse, they form protostars, which are surrounded by rotating disks of gas and dust, protoplanetary disks. It is in these disks that the conditions for planet formation become favorable. The chemistry occurring within these disks is complex and varied, as simple molecules collide and react to form more complex compounds, setting the stage for the development of diverse planetary bodies. Dust grains within the protoplanetary disks serve as the first seeds of planetary formation. These grains, made primarily of silicates, ices, and organic materials stick together through electrostatic forces and form larger clumps. This process of accretion continues until these clumps grow into planetesimals, which are the building blocks of planets. The size and composition of these planetesimals can vary greatly, leading to the formation of terrestrial planets, gas giants, and icy bodies depending on their distance from the star and the local environmental conditions. One of the most fascinating aspects of planetary system formation is the diversity of planetary architectures that emerge. Recent observations have revealed a broad spectrum of planetary system configurations, from systems dominated by a single massive planet to those with multiple planets and complex resonances. The existence of hot Jupiters, gas giants that orbit very close to their stars, has particularly challenged previous models of planetary formation, which suggested that such massive planets could not form in the inhospitable conditions near their host stars. These discoveries indicate that planetary migration plays a significant role in shaping the final architecture of planetary systems. The migration of planets can occur through various mechanisms, including gravitational interactions with the protoplanetary disk and interactions with other planets. For example, as a gas giant forms, it can scatter smaller bodies in its vicinity, causing them to either be ejected from the system or pushed into closer orbits around the star. This type of migration can explain the presence of hot Jupiters, as these planets may have originated further out in the disk before migrating inward due to the complex gravitational interactions in their early environment. Moreover, the study of exoplanets has shown that planetary systems can also evolve in response to external influences, such as passing stars or molecular clouds. These external forces can perturb the orbits of planets, leading to chaotic interactions that may ultimately reshape the system. The dynamical evolution of planetary systems is a field of active research, as scientists seek to understand how these external factors impact the stability and longevity of planetary orbits. Another critical aspect of planetary system evolution is the interaction between planetary atmospheres and their host stars. As stars evolve, they undergo significant changes that can have profound effects on the planets in their vicinity. For instance, during the red giant phase, a star's outer layers can expand to the point where they engulf inner planets, drastically altering their fates. Even if a planet survives this phase, it may experience intense radiation and stellar winds that can strip away its atmosphere, fundamentally changing its ability to support life. The long-term fate of a planetary system is also influenced by the life cycle of the star itself. As a star ages, its luminosity changes, which can affect the habitable zone, the region around a star where conditions might be right for liquid water to exist on a planet's surface. For example, as a star transitions from the main sequence to the red giant phase, its habitable zone moves outward, potentially rendering previously habitable planets uninhabitable as conditions become too extreme. This dynamic shifts the focus of astrobiological investigations as scientists seek to understand how planets adapt or succumb to the changing environments of their stars. As we consider the vastness of the universe, it's essential to address the possibility of life beyond Earth and the conditions necessary for its existence. The concept of the Goldilocks zone, the habitable zone around a star where temperatures are just right for liquid water, has been instrumental in guiding our search for potentially habitable exoplanets. However, the understanding of habitability is rapidly evolving. Recent discoveries suggest that planets outside this zone may still harbor conditions conducive to life, such as those that might exist on icy moons like Europa or Enceladus, where subsurface oceans could provide the necessary environment for life to thrive. The exploration of these potential habitats has been greatly enhanced by robotic missions within our solar system. For example, the Europa Clipper mission, set to launch in the 2020s, aims to study Europa's icy shell and subsurface ocean, searching for signs of habitability. Such missions not only enhance our understanding of our own solar system but also inform our investigations of distant exoplanets, where we seek to identify biosignatures that might indicate the presence of life. In our quest to understand planetary systems and the potential for life beyond Earth, we must also grapple with the ethical implications of our discoveries. The search for extraterrestrial life raises profound questions about humanity's role in the universe and the responsibility that comes with our explorations. As we advance our technological capabilities and push the boundaries of our understanding, we must consider how our actions might impact other worlds and their ecosystems. The ongoing exploration of planetary systems is a testament to human curiosity and ingenuity. The questions we ask and the discoveries we make drive our understanding of our place in the universe. As we forge ahead into this uncharted territory, we must remain committed to the principles of scientific inquiry, collaboration, and stewardship of our cosmic environment. The journey into the mysteries of planetary systems is far from over, and with each new revelation, we are drawn closer to understanding the grand tapestry of the universe and our role within it. In conclusion, the formation and fate of planetary systems is a complex interplay of cosmic forces, chemical processes, and astronomical events. From the birth of stars and the subsequent creation of planets to the interactions that shape their evolution, each aspect contributes to a greater understanding of the universe. As we continue to explore the cosmos and seek answers to the fundamental questions of existence, we are reminded that we are but one small part of a much larger story, one that encompasses the birth, life, and death of countless worlds, each with its own narrative woven into the fabric of the universe. This journey invites us to look beyond our own planet and consider the potential for life in the vast expanse of space. With every discovery, we not only expand our scientific knowledge but also deepen our philosophical reflections on what it means to exist in a universe filled with wonder and mystery. The ongoing quest to unravel the secrets of planetary systems will undoubtedly shape our understanding of the cosmos for generations to come, as we continue to seek out the unknown, challenge our assumptions, and explore the infinite possibilities that lie ahead. As we delve deeper into the complexities of planetary systems, it becomes increasingly clear that the journey from the initial formation of planets to their eventual fate is not just a tale of physical processes, but also one intertwined with the fundamental laws of physics and the intricate dance of forces that govern the universe. The formation of planetary systems begins with a nebula, a massive cloud of gas and dust, where gravitational forces trigger the collapse of certain regions, leading to the birth of stars and the subsequent formation of protoplanetary disks. The dynamics within these disks are influenced by various factors, including turbulence, temperature gradients, and magnetic fields. These elements play a crucial role in determining the distribution of material and the eventual architecture of the planetary system. For instance, the temperature distribution within a protoplanetary disk causes a distinction between the inner and outer regions. Closer to the star, the heat can evaporate volatile materials, leading to the formation of rocky planets like Earth and Mars. In contrast, the cooler outer regions allow gas giants, such as Jupiter and Saturn, to form, capturing abundant hydrogen and helium from the surrounding disk. As these planetary bodies grow, the interactions between them can lead to a variety of outcomes. Planetary migration is a key process, wherein planets can change their orbits due to gravitational interactions with the disk material or with each other. For example, a massive planet that forms in the outer regions may migrate inward, disrupting the orbits of smaller bodies and potentially leading to the formation of a more chaotic system. This migration can also result in planets becoming locked in orbital resonances, which can have lasting effects on their atmospheres and geological activity. The concept of planetary resonances is particularly fascinating. When two or more planets exert gravitational influence on each other, they can enter into resonant orbits where their orbital periods are related by a ratio of small integers. This phenomenon can stabilize or destabilize their orbits, leading to enhanced geological activity or, conversely, preventing the accumulation of debris that might otherwise pose a threat to the planets involved. The interplay between these forces exemplifies the intricate ballet of celestial mechanics at play within planetary systems. As we examine the fate of planetary systems, it's crucial to consider the life cycle of their parent stars. The evolution of a star directly impacts the planets that orbit it. For example, our Sun is currently in the middle of its life cycle, undergoing nuclear fusion and radiating energy that creates the conditions for life on Earth. However, as it exhausts its nuclear fuel, it will expand into a red giant, engulfing the inner planets and potentially transforming the outer planets' orbits. The fate of these planets will depend on their initial distance from the Sun and the subsequent changes to their environments as the Sun evolves. Moreover, the role of stellar companions in planetary system evolution cannot be understated. Many stars are part of binary or multiple star systems, where the gravitational interactions between stars can have profound implications for the planets that orbit them. For instance, the presence of a massive companion star can alter the orbits of planets significantly, potentially leading to ejection from the system or forcing them into unstable trajectories. The unique gravitational environment in these systems can result in diverse planetary configurations that differ markedly from those in single-star systems. In addition to stellar companions, external forces such as galactic tides and passing molecular clouds can also influence planetary systems. The gravitational pull from neighboring stars can disrupt the orbits of planets, leading to chaotic interactions that may result in collisions or ejections. These perturbations can shape the long-term stability of planetary systems and provide insights into the dynamic nature of the galaxy. As we consider the implications of these forces on habitability, we begin to understand the delicate balance required for a planet to support life. The presence of water, a stable atmosphere, and a suitable climate are essential ingredients for life as we know it. However, these conditions can be easily disrupted by changes in a star's behavior or by interactions with other celestial bodies. Understanding these dynamics is vital for identifying exoplanets that might harbor life, as we search for worlds that exist within the habitable zones of their stars. The search for extraterrestrial life has become one of the most exciting frontiers in contemporary astrophysics. Scientists are employing increasingly sophisticated technologies to detect and characterize exoplanets, particularly those that lie within the habitable zones of their stars. The transit method, which involves observing the dimming of a star as a planet passes in front of it, has proven to be particularly effective in identifying potentially habitable worlds. Missions like the Kepler Space Telescope have discovered thousands of exoplanets, many of which challenge our previous notions of planetary formation and habitability. Moreover, the advent of direct imaging techniques allows astronomers to capture images of exoplanets and analyze their atmospheres for potential biosignatures, chemical indicators of life, such as oxygen, methane, and water vapor. The upcoming James Webb Space Telescope promises to enhance our ability to study the atmospheres of exoplanets, bringing us closer to answering the age-old question, are we alone in the universe? The possibility of life beyond Earth also raises intriguing philosophical questions about our place in the cosmos. As we uncover more about planetary systems and the conditions necessary for life, we must consider the implications of our discoveries. If we find evidence of extraterrestrial life, how will that alter our understanding of humanity's role in the universe? Will we embrace the interconnectedness of all life, or will we struggle to reconcile the existence of other intelligent beings with our own self-image? As we contemplate the fate of planetary systems, we cannot overlook the impact of human activity on our own planet. The study of planetary systems serves as a reminder of the fragile nature of planetary environments and the importance of sustainability. Our actions on Earth have far-reaching consequences that can alter not only our planet's future but also our ability to explore and inhabit other worlds. As stewards of our planet, we must prioritize the health of our ecosystems and the well-being of future generations, recognizing that our choices resonate far beyond our immediate surroundings. In summary, the formation and fate of planetary systems is a multifaceted narrative that intertwines the physical processes of the cosmos with the philosophical questions of existence. From the birth of stars to the potential for life beyond Earth, our exploration of these topics invites us to reflect on our place in the universe. As we advance our understanding of planetary systems and the forces that shape them, we uncover the profound complexity and interconnectedness of the cosmos, reminding us that we are all part of a grand story that transcends time and space. As we conclude this exploration of planetary systems, we are left with a sense of wonder and curiosity about the universe and our place within it. The mysteries of formation, evolution, and the potential for life in the cosmos continue to captivate our imagination, driving our quest for knowledge and understanding. The journey ahead is filled with possibilities, as we look to the stars and seek answers to the fundamental questions that define our existence. With each discovery, we step closer to unraveling the intricate tapestry of the universe, revealing the beauty and complexity that lies within. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.